And we're back again to continue filling out the worksheet for section 11.2 on Introduction to Series. So this section is going to deal with telescoping series, the harmonic series, and the beautiful test for divergence. Okay, good. So what's the definition of a telescoping series? Well, telescoping series will take the form of the sum of terms AK plus 1 minus AK, or if we've got AK coming first, then we subtract AK plus 1. So we're looking at these types of forms here. And we want to look at if we can express our series that we need to determine convergence or divergence of, then we'll want to see if we can express it in that form and then use the rules for that. So what is that telescoping series test, and how can we determine if a telescoping series is convergent or divergent? So I've already taken the liberty of writing out what the test is and how to verify based on the definition of a convergence series. So what is this telescoping series test? If we have a telescoping series, and we'll just take the first form, AK minus A sub k plus 1. And if the limit of the second term, AN plus 1, exists, in other words, if it converges to a limit, a finite number, then your telescoping series will converge, and the sum of that series will be A sub 1 minus L. So here's the motivation behind that, or the reasoning behind that. So what does it mean for a series to converge? If the sequence of partial sums converges to a limit, which is a finite number, and that finite number would be the sum of your series. So here I go creating the expression for the partial sum of this telescoping series. So when k is equal to 1, our very first term is A sub 1 minus A sub 2. And when k is equal to 2, and I'm going to add that together, it's going to be A2 minus A3. And when I add k equal to 3, that's going to be A3 minus A4. And then if I continue to add these numbers up through n, because we're finding the partial sum S sub n, I've got that the nth term would be A sub n minus A sub n plus 1. So if I add the clear parentheses and add all of those terms together, we see that the entire sum for that partial sum collapses to the very first term, A sub 1, and then minus A sub n plus 1. So if that's my expression for S sub n, remember what it means for a series to converge if the sequence of partial sums converges. So if I take that limit of the S sub n, that's going to equal the limit as n goes to infinity of A sub 1 minus A sub n plus 1. And A sub 1 in this term, or in this expression, is a constant, and the limit of a constant is that constant. And we also know from limit laws that the limit of a difference is the difference of the limits. So we just now have to calculate the limit as n goes to infinity of A sub n plus 1. So if that limit actually exists, then the sequence of partial sums converges to A sub 1 minus L, and that would be the sum of the series. So if the limit of A sub n plus 1 does not exist, then the limit of the sequence of partial sums does not exist, and then we would have a divergence series. Good. So taking a look back at example A, the sum of 1 over k times k plus 1 doesn't look like it takes the form of a telescoping series, but we can go back to what we learned in chapter 7 and express 1 over k times k plus 1 in terms of partial fraction decomposition. So let's remember how we do partial fraction decomposition. I'm going to say 1 over k times k plus 1. That's going to equal an A over k plus a B over k plus 1, because we do have a proper rational expression. It's already completely factored. When I multiply on both sides by the large denominator on the left, I end up with 1 equal to A times k plus 1 plus B times k. And when I choose particular values of k, In particular, if k is equal to minus 1, we have 1 equal to 0 times a minus b times, or minus b. And so we end up with minus b equal to 1, or minus 1 is equal to b. Second, if we take k equal to 0, we end up with 1 equal to a times 1 plus b times 0, or 1 is equal to a. So then we can rewrite the 1 over k times k plus 1 as equaling 1 over k plus, and then we have the negative 1. So we can actually erase that plus and say that this is equal to minus, and we have the 1 over k plus 1. Good. So then we can say that our series is equal to, from k equal 1 to infinity, of 1 over k minus 1 over k plus 1. And now we have the telescoping series form. And we can say that this is a telescoping series. So, in employing the test, I can say if the limit as n goes to infinity of 1 over k plus 1 exists, then we have that our series converges, right? And so in calculating the limit as n goes to infinity of 1 over k plus 1, or this should be a k, sorry, then that's going to go to 1 over infinity plus 1, which is going to 0. So by conclusion, our series 1 over k times k plus 1 converges, and the sum is equal to a sub 1 minus 0, right? And my a sub 1 is actually going to be 1. 1 over 1 minus 0, which is 1. Good. So there you have it for telescoping series. And that's kind of fun. We have a second one that I might let you guys play with. Hint, we do have that this is going to equal k equal to 3 to infinity of ln of k plus 2, take away the ln of k plus 1. And we could factor out the negative 1. Remember, we've got a constant. So we can say that this is equal to negative k equal to 3 to infinity of ln of k plus 1, take away the ln of k plus 2. So we do take the form of a telescoping series. And we can then take our limit as k goes to infinity of ln of k plus 2. And we see that that's going to the ln of infinity plus 2, which is going to infinity. So the limit does not exist. So our conclusion here then will be my series k equal to 3 to infinity of ln of k plus 2 over k plus 1 diverges, because the sequence of partial sums for that will diverge as well. Because it would diverge, it would be a sub 1, which would be, or a sub 3, which would be ln of 4 take away infinity, and that is still infinity. So we have a divergent series. Okay, next up, this type of series called the harmonic series is going to be a very important example or very good type of series to use for the up-and-coming comparison tests. We will also revisit harmonic series when we discuss the integral test for convergence and demonstrate that we can show that this harmonic series will diverge as well. It also is an example of one that demonstrates some qualities about the test for divergence. All right, so in this proof that the harmonic series diverges, we actually use the formal definition of a convergent series, which is we set up a sequence of partial sums. It is in the proof using the fact that we're really, if a sequence converges, or if we've got a sequence that has a limit, every subsequence is going of that sequence is going to converge to the same limit. In other words, we can take a portion or a subsequence of the entire list of numbers, and that's going to converge to the same limit. So if we have a divergent sequence of partial sums, the subsequences of partial sums are also going to diverge, and vice versa. If the subsequence of partial sums diverges, then the big function or the big sequence also diverges. So they kind of use a little bit of a trick. So what is this harmonic series? It's the sum of 1 over n. So if we replace starting with n equal to 1, that would be 1 over 1 plus 1 over 2 plus 1 over 3. And this sequence, or this series, is going to diverge. So we first come up with a subsequence of partial sums. And so remember what a partial sum is. It's the first sum of the first couple terms. So if we take a look at s sub 2 to the first power, that's just going to be s sub 2, and that's going to be the sum of the first two terms. Then we go to s sub 2 squared, which is s sub 4, and we're going to take the sum of the first four terms. And then s sub 2 to the third would be s sub 8, and we're going to take the sum of the first 8 terms. And so we're forming a pattern here, and we're forming a structured subsequence of partial sums. And we're going to show that that actually goes to infinity. So we first say s sub 4 is 1 plus 1/2 plus 1/3 plus 1/4. And we keep the 1/2, but we take the 1/3 and the 1/4. Remember, the bigger the denominator, the smaller the number if the numerators are the same. So 1 divided by 3 is bigger than 1 divided by 4. And then we take the 1/4 plus 1/4 is 1/2, and 1/2 plus 1/2 is 2/2, and we see that s sub 4 is equal to 1 plus 2/2. And then we take a look at s sub 2 to the third, which is s sub 8, and we're going to do the same type of pattern. We're going to say that that equals 1 plus 1/2, and then we're going to group these terms together. We're going to say, and let me highlight, we're going to take the 1/3 and the 1/4, and we're going to use 1/4, right? And that's going to be bigger. And then we're going to take the 8, and we're going to turn all of these into 1/8. And notice that the 1/4 plus 1/4 is 2/4, which is equal to 1/2. And the 1/8 plus 1/8 is 4/8, and that's also going to be a 1/2. So you get the idea. And then we have 1/2 plus 1/2 plus 1/2 is 1 plus 3/2. And then just to see that it overall establishes that pattern, we have s sub 16. So again, we're going to take that 1 plus 3, 1 plus, or 1/3 plus 1/4, 1/5 all the way up to 1/8, and we're going to say the 1/9 all the way up to 1/16. And you'll see again, that's what we're going to be doing here, and we end up with 1/2 plus 1/2 plus 1/2 plus 1/2, and that's going to give us the 4/2, right? And notice here that this is s of 2 to the 4th power, and if we notice, this 3 is going to be this 3 over here, and this 2 is going to be this 2 over here, and we have that this 4 is this 4 over here. So we can say similarly, s to the 2 to the 2 to the 5th power is s sub 32, and that's going to be greater than 1 over 5 over 2, or 1 plus 5 over 2. And s sub 2 to the 6th is going to be greater than 1 plus 6 over 2. So in general, we see that s sub 2 to the n is going to be bigger than 1 plus n over 2. So now, if we've got a subsequence of partial sums, and the limit as n goes to infinity of s to the 2n is going to be the limit as n goes to infinity or greater than, sorry, that's going to be greater than the limit as n goes to infinity of 1 plus n over 2, and that's going to go to 1 plus infinity divided by 2, which is infinity. So our limit of our subsequence goes to infinity, and so we say that it is divergent. Good. So we do use, this is just an example of the harmonic series. So please note that the sum or the infinite sum of 1 over n is divergent. Okay. So now it comes to the final thing, our final topic in this video, and this is the test for divergence. So the theorem here says that if the series a sub n is convergent, then it has to be the case that the limit of the sequence of just the a sub n's, this is not the partial sums, this is just the limit of the terms, has to eventually go to 0. So here's the proof of that. So suppose the a sub n's, the series a sub n does converge. So a1 plus a2 plus a3 plus dot 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 plus a sub n plus dot 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 forever actually converges. Well, then that means the limit of the partial sums converges. And if that converges, it's going to converge to a finite number. So let's call that number S, right? And S sub n is that nth partial sum. So we rewrite a sub n as, if I take the partial sum S sub n, we know that that's 1 plus, or a1 plus a2 up to a sub n. But if I take the partial sum S sub n minus 1, it's up to the ones right before. So if I just take S sub n minus S sub n plus 1, that's going to equal a sub n. Good. And so if I take the limit of the a sub n, then if I just replace the s sub n minus the s sub n minus 1, remember s sub n minus 1 is a subsequence of s sub n. And if the s sub n converges to s, then the subsequence is also going to converge to s. And we know that the limit of a difference is the difference of the limits, and they both go to the same limit. And so we do have that limit is going to be equal to 0. So if our series is convergent, then the limit of the a sub n's better go to 0. The converse is not always true, but it does mean that the limit going to 0 is definitely necessary, but it's not a sufficient condition. Why? Note here that, and I do want to continue highlighting, but it's not a sufficient condition. Note that the sum, or the sum of 1 over n as n equal 1 to infinity diverges, right? But the limit of 1 over n as n goes to infinity is 0, right? So just because the limit of the an's goes to 0 does not mean that your series is going to converge. It's just a necessary criteria. So those of you who've taken a logic course, if we do have, this brings rise to our test for divergence. And remember what the title of that test is. It's just a test to determine if the series diverges. It cannot be used as a test for convergence, but you can use it to say that a series does diverge. So from logic, we know, suppose A implies B is true. Then the contrapositive is also true. And what is the contrapositive? Then if not B, then not A. Not B is going to imply not A. So if we take a look at this is the A implies B. So if your series is convergent, so if that's my A, then is my implication, and this is my B, then the test for divergent is what is the opposite of limit does not equal 0, right? So this portion down here is not B, which is not B is the limit of the A sub n does not equal 0, right? As n goes to infinity. So if it's not equaling 0, then the limit either does not exist, which is plus or minus infinity, or truly oscillating back and forth does not exist, or just simply it goes to a different number, so it's not equal to 0. Then, and then this portion over here, then the series is divergent, and this is not A from above. Good, so this is simply just the contrapositive of the proof that we just did above. Okay, now I tend to use this as my very first, because what we're leading up to is a series of convergence and divergence tests for various infinite sums. So bear with us, we just covered 2 of them. And what are those 2? The geometric series test and the test for divergence. Good. So in this case, what is our A sub n? Remember that our A sub n will always be in a series, the entire expression. So in this case, this is the sum of A sub n, and so A sub n here is minus 1 to the n. So, and using the test for divergence, I can say, does the limit as n go to infinity of A sub n not equal 0 or does not exist? And remember, the does not exist is plus or minus infinity, or really does not exist. So I'm looking at what is the limit of my A sub n as n goes to infinity. That's going to equal the limit as n goes to infinity of minus 1 to the n, and that's going to go to minus 1 to the infinity. So that is oscillating between minus 1 and 1 forever. And so we really say that this limit does not exist. So what is our conclusion? We say, therefore, my series, negative 1 to n from n equals 0 to infinity, diverges by the divergence test. Good. We can take a look at this example, and we can see that this is our A sub n, and the limit as n goes to infinity of 9 plus n squared over 3n squared plus n minus 2. You can either factor out the highest power of n or use L'Hopital's rule twice. And just factoring out the highest power of n, we've got n squared times 9 over n squared plus 1 over n squared times 3 plus 1 over n minus 2 over n squared, right? Got to divide out by n squared to all terms. And if I factor out equal magnitudes of infinity and then use my limit laws, 9 over n squared is going to go to 9 over infinity, which is 0. 1 is going to go to 1. 3 is going to go to 3. 1 over n is going to go to 0. And 2 over n squared is going to go to 0. So this limit is going to go to 1 over 3, right? So we have, since the limit of the A sub n is equal to 1 over 3, which is not equal to 0, then our series diverges by the divergence test. Good. Okay. This one, how would you use this one? We see here, since this is going to be our sum of the A sub n. If the limit of the a sub n here as n goes to infinity is going to be the limit of k plus 2 over k plus 1 as n goes to infinity, or ln, sorry. The ln of k plus 2 over k plus 1 as n goes to infinity. And that's going to equal the ln, since the ln is a continuous function, of the limit as n goes to infinity of k plus 2 over k plus 1. And that is actually going to go to the ln of 1, which is 0. So the limit of the a sub n is equal to 0. So conclusion, no conclusion. With the divergence test. So we must pick a different test. Oop. Oop. Sorry, different test. And recall the telescoping series from above. Good. All right. So finally, we end with some properties for convergent series. If a sub n and b sub n are convergent, then so are the series a constant times the a sub n, or the sum a sub n plus b sub n, or the difference a sub n minus b sub n. So I kind of look at this as the algebra of convergent series, so we can take them one step at a time. And if you ever have any of them divergent, then the whole series is going to be divergent, because you have to think of the sequence of partial sums converging. So if any one of, if say for instance b sub n is divergent, then the sum of a sub n plus b sub n is going to be divergent. So you can take a look at this and set up for next time. Maybe we will do this in office hours, but remember that we can say this is equal to k sub equal to 0 to infinity of 2 to the k plus 1 over 4 to the k plus, or minus, sorry, minus 5 over 4 to the k, just using our algebra. And then we can split up by saying this is equal to k equal to 0 to infinity of 2 to the k plus 1 over 4 to the k, take away 5 times the sum from k equal to 0 to infinity of 1 over 4 to the k. And we would want to employ our geometric series tests. And so I can say that this is equal to k equals 0 to infinity of 2 times 2 to the k over 4 to the k. And over here, I can rewrite this as k equal to 0 to infinity of 1 over 4 to the k, because I can rewrite 1 as 1 to the k and then use my exponent laws there. This repeats to, or reduces to 2 times 1/2 to the k, and putting the 2 to the k over 4 to the k into 1 fraction 2 over 4 to the k, and I end up with 1/2 minus 5, k equals 0 to infinity of 1/4 to the k. Both of these are of the form a times r to the k from k equals 0 to infinity, minus 5 times a times r to the k from k equals 0 to infinity. And I see here from the geometric series that both of them are convergent, because I see in this case a is equal to 2, and absolute value of r is equal to absolute value of 1/2, which is less than 1. So we would have that this is equal to 2 over 1 minus 1/2. And then we have minus 5. And in this case, we do have a here is equal to 1, and r here is equal to 1/4. And this is going to be 1 over 1 minus 1/4. And if we multiply through, we do get this is equal to 4 right? Because 1 minus 1/2 is 1/2, and 2 divided by 1/2 is 2 times 2 over 1, which is 4. And then we have minus 5, and here this would be 1 divided by 3/4, and that would be 4/3. Good. And then, and looking at that, we can say that this is 12/3, take away 20/3, and 12 minus 20/3 is equal to minus 8/3. And so that is going to be the sum of our series. Good. And we can say that it is convergent. So I encourage us to do example B. Possibly we will do that in office hours. And I hope you enjoyed this series.